Hi class, what I want to do in this short screencast is to go over the ICE problems pertaining the weak acids one more time and try to connect them again with the percentage ionization and how to determine the pH. The question here is, determine the pH of 0.100 molar HCN solution. Recall HCN is hydrocyanic acid, and the fact that we have a Ka given to us as 4.9 times 10 to the negative 10, so that's a really small Ka, and that tells me that this must be a weak acid. Recall any K value less than 0.001, that automatically means the backward reaction is more predominant and it's going to be a weak acid or a base, as the case may be. So in this case, if we are saying that it's a solution, we always say that this is an aqueous solution. So the first thing you should be doing is take HCN, aqueous, and add water to it. The water that you're adding obviously is in the liquid phase, and that would be in equilibrium. This is the hydrocyanic acid, so that's the one that's going to deliver the protons, and that proton will be picked up by water to give you hydronium ion, and that's what makes it an acid. Cyanide is the conjugate base. So you can hopefully visualize that this is the acid, this is the base. Conjugate acid is the hydronium ion that gets generated, and cyanide is the leftover of the HCN, so that's my conjugate base. Now, when you're ready to set up the ICE problem, initial, change, and equilibrium, realize you will need the initial concentration, which in this case has been given to be 0.100 molar concentration. Realize this is a weak acid, so as you put the hydrocyanic acid in the water, in the beginning the concentration of hydronium ion and the concentration of the cyanide, as we discussed in class, that's going to be 0, and the reason for that is because you've basically caught the reaction right at T is equal to 0. So at that time no products have been generated, and that is the reason we say that the hydronium ion concentration as well as the cyanide is going to be 0. Now, this is a balanced equation, so if the change occurs by x moles, so let's say x moles of the hydrocyanic acid go through this dissociation to generate x moles of hydronium ion and x moles of the cyanide. And equilibrium, recall from class, was just the addition of the initial and the change. So equilibrium concentrations will be 0.1 minus x, or 0.100. Let's keep the significant figure intact. This is going to be x, and the cyanide is going to be x as well. Once you have set up your ICE, the next step is to basically plug in all the numbers into the Ka value. So I'm just going to change the color so that we can view that. I don't want to erase things yet. Ka is going to be equal to hydronium ion concentration times cyanide, and the power in this case is going to be 1 because there's no stoichiometric coefficients here. Well, it's 1. And we divide it by HCN. Again, we drop the H2O because that will not contribute to the equilibrium constant value. It's a liquid. And so now I'm going to simply plug in the values. So x times x divided by 0.100 minus x, and that number should be equal to the 4.9 times 10 to the power of negative 10. Now one might ask, can we actually use the approximation, or should we use the solution to the quadratic? And the answer to that lies in the fact that, well, you have to determine for this particular problem the initial concentration that is given to you, which is 0.100, divided by the Ka value. What does that reveal? So at some point in some space, let me erase just some parts so you can see better. What I'm trying to calculate is 0.100 divided by 4.9 times 10 to the power of negative 10 and determine whether this number, verify whether this number is more than 100 or not. And if it is, then you would be able to use the approximation. Use approximation. And then the approximation is that the x is so small that you can simply omit that out. And so your equation will start looking more like x squared. Let me erase the i's. I don't want to get rid of the question yet. So it's going to look like x squared divided by 0.100 equals 4.9 times 10 to the power of negative 10. And now when you plug in the numbers, it's going to look like, or rather solve for x, you're going to see that it will be 49 times 10 to the power of negative 12, or x is equal to square root of 49 times 10 to the power of negative 12. And you can do all of that together on the calculator. I'm just doing that stepwise. Minus 7 molar is what I got for x. But recall, what was x? When we set up the ice problem, x was the hydronium ion concentration as well as the cyanide. So realize that I have basically determined the value of the hydronium ion concentration as well as the cyanide by solving this ice problem. And you know that pH is nothing but negative logarithm of the hydronium ion concentration. So one can safely say negative logarithm of 7 times 10 to the power of negative 7. I'm sorry, negative 6, not negative 7, negative 6, it was 12. Negative 6 is going to give you the value of pH. So that in this case, if I can put that on my calculator, and I got a value 5.15. So that's my pH. Let's say I want to determine, so in this case the question was just to determine the pH, but let's say the question would also expect you to determine the percentage ionization. What would you do then? Before I do that, let me erase parts of the things of this question so that I make room. I have determined that the hydronium ion concentration, H3O plus, is 7 times 10 to the power of negative 6 molar. I determined the pH. The percentage ionization is given by the amount that dissociated. So HCN that dissociated, divided by the total, divided by the initial that you began with, times 100. Realize that the amount of HCN that dissociated is what is responsible for this hydronium ion that gets generated in my solution. And so once you have determined the value of the hydronium ion at equilibrium, which was 7 times 10 to the power of negative 6, simply by dividing that number by the initial concentration, which was 0.1 times 100, will give me the percentage ionization. So on my calculator, I'm going to plug in 0. Divided by 0.1, and that gives you 7 times 10 to the power of minus 5 as your final answer. So 7 times 10 to the power of minus 5, not molar. That's the percentage ionization. So realize this number is like a really, really tiny number. This number is a very small number. That number is in percentage. And that tells you that HCN is an extremely weak acid that we have. There was a statement that I made in class, and what I said was that when you have a weak acid such as, let's say, nitrous acid, HNO2, which has this one proton that can be given off. So that's what's common between HNO2 and HNO3. Both of these have only one proton to give off. But nitric acid is an ic acid, and so that makes it a strong acid. But the question that I want to ask here is, going back to what I said in class, that if you have a weak acid and if you wanted to sort of increase the extent of ionization. In other words, if you wanted to increase the percent ionization, then you will need to keep the concentrations down, the concentrations low. Let's say if you are able to actually prove this point by looking at this comparison. What I want you to do is determine the percentage ionization of a 2.5 molar concentration of HNO2, and I want you to compare that to 0.2 molar HNO2. In both of these, realize that the reaction that we have is the same. We have HNO2, which is reacting with water, and nitrous acid, being the acid, is going to generate H3O plus, and NO2 negative is what is going to get generated. So you're going to set up an ice for both of these. Realize when the initial concentration, that's for HNO2, that's 2.5. Hydronium and nitrite, both of those are 0. If the change is by X, then you get X moles of each of these. So over here you have 2.5 minus X, over here you have X and X. And so now if you had to set up the Ka, you're going to say that that's going to be X times X divided by 2.5 minus X, because water is not going to feature in the equilibrium, and the value for Ka for nitrous acid is a really small number. Let me just pull that from this table here. That number is 4.6 times 10 to the power of negative 4. So you have a relationship x squared divided by 2.5 minus x equals 4.6 times 10 to the power of negative 4. And you have to ask yourself whether or not you can actually take a look at the approximation and use the approximation, really. So you're going to find out the ratio of the initial concentration that you have, which is 2.5. So 2.5 divided by 4.6 times 10 to the power of negative 4. That's going to give you a number which is greater than 100. I can just tell that by looking at it. And so the x can be deleted. So really you're just looking at x squared equals to 4.6 times 10 to the power of negative 4 times the 2.5. So that comes out to be 1.15 times 10 to the power of negative 3. Or you could have just written that as 11.5 times 10 to the power of negative 2. So when you take a square root of that, let's take a square root. This calculator has one. Okay, and that comes out to be 3.39 times 10 to the power of minus 2 molar concentration. So that's the value of x that I got from the high concentration of 2.5. I want you to do the same thing so set up the ice for the lower concentration, which will be 0.2, and I really want you to do this. And I'm just going to write down what it'll look like. The Ka in this case is going to be x squared divided by 0.2 minus x is equal to 4.6 times 10 to the power of negative 4. Here too it is valid, and so you can determine the value of x, and that value comes out to be 9.6 times 10 to the power of minus 3. Is that right? So now if you wanted to determine the percentage dissociation in case of the lower concentration, you would simply say that that's going to be 9.6 times 10 to the power of negative 3 divided by 0.2, because that is my initial concentration, times 100. And that number comes out to be 4.8%. On the other hand, if you do the same thing for the concentration that we determined, so 0.0339 divided by 2.5 times 100, and that number actually comes out to be a much lesser value, 1.4%. And so hopefully you can see and appreciate that as you dilute the solution, or if you keep the concentrations lower, the weak acid is going to remain much better ionized. The last thing that I want to cover is if you have a solution of, let's say, acetic acid, CH3COOH with water, and we are going to discuss this again in the next chapter, but I just want you to get started. I just want you to think about something that we already have discussed actually in the chapter on equilibrium through Le Chatelier principle. And let's say this is my ionization reaction. And I want to add acid to this equilibrium, right? And I want to add, let's say, HCl, which by the way is a strong acid and gives you lots of protons. That means I'm increasing the concentration of the hydronium ion right here. And so if you're increasing the concentration of the hydronium ion, hopefully you can visualize according to the Le Chatelier principle, the equilibrium should move it in the direction so as to undo that change, and so it should keep it backward. So more and more acetic acid would remain undissociated in such a solution.